Hello people and welcome to another video of Programmer's Corner. In this video we are going to take a look at how to implement Radix Sort using a height balanced binary leaf search tree. So a quick disclaimer out there that if you want to take a look at how to implement the actual base of Radix Sort where we create 10 buckets and how we put numbers in there, you probably want to go and watch the previous video. The links in the description below. In this video we are just going to take a look at the main structuring of the binary tree, how the height balancing works, how the left rotation, right rotation works, how the insertion and deletion works. So let's begin. There are a few properties of height balanced leaf trees that one should take into consideration before you construct or program it. So the properties are as follows. In a leaf tree, all the data is stored in the leaf nodes, while the interior nodes or the non-leaf nodes are mere comparison nodes. So if you want to insert something in a binary leaf tree, the non-leaf nodes are more of a comparison where whether you want to go to the left or you want to go to the right of a given from a given node. Now that in mind, a height balanced tree has the following properties, and that is the height of the leaf nodes is always 0. The height of the non-leaf node is the maximum among its children node plus 1. So in this case, if you take the node, if you take this node, the height of this node is going to be the maximum among these two, that is 0 and 0. The maximum in this case is 0, and you add a 1 to it, so now the height is 1. The same thing goes here. The height of this node is the maximum of these two, that is the maximum in this is 1, so you add another 1 to it, so now it becomes 2. In this case it's the maximum of these two, so now the maximum here is 2. You add 1 to it, it becomes 3. So keeping this in mind, we'll look at how to do insertion and deletion of a given tree, and while insertion, how do you balance it using the height from a given node. So now the third clause here is that how do you consider whether the tree is balanced or not? So for that there are three cases. The three cases are as follows. If you take a node of a tree, the tree from that node down below is considered to be balanced if the difference between the height of its children is either 0, 1 or minus 1. So in this case the difference between the height of its children is 1 minus 2, that is minus 1, so it's between the range. Here is 1 minus 0, that is 1, so here it is in the range, and here it is 0 minus 0, that is 0, so here also it's in the range. So we can say that on each and every node, the tree down below from that node is balanced because it hits in the range of minus 1, 0 or 1. So now keeping that into mind, we'll take a look at how to do an insertion on a given tree, and then we'll also see how we do the balancing when we actually do the right balance, actually do the left rotation or the right rotation. So now let's say I want to insert a node, or I want to insert a key 24 into this tree. So now I start from here and I compare, is 24 greater than 20? Then I go to the right. Is 24 greater than 30? No, then I go to the left. Is 24 greater than 21? Yes, I go to the right. Is there anything below that I can go to? Well, I cannot. So now this is the point where I'm going to insert. So on insertion, I'm going to do the following. I'm going to split this node into two. So what I'm going to do is I'm going to make a new node. I'm going to make two new nodes. I'm going to check. I'm going to make this one as 21 and this one as 24, because 24 is greater than 21, so it's going to go to its right, and this node is going to change to 20. The key and this node is going to change to 24, and now we have to change the height of it. Whereas you have to keep one more thing. You have to keep one more thing into consideration, and that is, as we go down the tree, we also keep the nodes that we have visited previously onto a stack, so that once we are done inserting, we visit the stack, get the nodes that we went down through, and then we rebalance using those nodes. Now here at this point, the height of this tree is now, the height of this node is now going to be 0 because there are two children, it has two children nodes. So the height is going to be the maximum of these two in this case is 0, so the height is going to be 1, because the maximum plus 1. So now once we are done with this, I have to do the connections. Now once we are done with this, now we go back up here and we see if the given rotation is, if the given tree from down below here is balanced or not. There is one more thing that I have to tell you, and that I have done in this case, is that what if there is a repetition in the keys? So in a binary tree, if the key already exists in a tree, what I do is I just return a -1 because I do not do any insertion. But in this case I cannot do it. So if there is a repetition in the key, each node here has another variable called occurrence, which increments the occurrence of that number. So let's say if a tree has a number key 21, and if it inserts another 21, it goes here and it does not split the node. Instead, it increments the occurrence at this node, saying that there are 2 occurrences of the number 21. Now coming back to the insertion, we have inserted 24 at this point. So now we pop another one from the stack. So now we are at this node, at node with key value 21, and its height is 1, which we have to again change based on its new inserted children nodes. So now that we are at this node 21, we see whether what's the difference between the heights of its children. So at this point, the difference between the height of its children is -1. So what we do is we go here and we see, well, the height is not equal to 2. Well, the left and the right difference of the height is not 2, it's actually -1. So it's not going to go here, it's not going to go to this else statement, instead it's going to go here. So now what we do is we check which height is greater, and we see that the right height is greater than the left height. So we take this height and we add 1 to it. So now the height at this node is going to be 2, and it's still balanced. Now we pop another node, that is this node, and we check we do the same thing. So now we check is that what's the difference between the height of its children. In this case it's 2, and it's out of the range, it's not in the range, it's neither -1, 0 or 1. So what we do with in this cases, we know that it is +2, so we check if the left's height, if from here the left height, which is 0, minus the current node's right height, its right height, child's height, and that's also 0, so it does not hit, it's not 1. So we go to the else part and we rotate the left tree. We do a left rotation with its left node, that is, we take this node and we do a left rotation on it. So with this, what we do is we go to the left rotation code and we keep track of, actually I have the code here, so we go to the left rotation code and we make this variable as a temporary variable or as a temporary node. We store the key as a temporary key, and we store the occurrence. In this case it's just only one occurrence. Then we set the left to right. So now this points to this and all this points here. And now this points to null. Oh, sorry, this is still pointing to this. So now we have 2 things pointing to the same thing. And then the ends key is the right key. So now this becomes, so this key becomes the right key. So now this becomes 24. And the occurrence also changes. Now the ends right becomes the ends left right. So the ends right becomes the ends left right, that is this node. And I don't need this anymore. And the ends left becomes the ends right becomes the ends left right, and the ends left becomes the ends left. The ends left right becomes the ends left. So now this becomes 24. this goes here, and the ends left becomes the temp key. That's this, and the ends left key becomes the temp key, which I have previously stored here, which was 21, and the end left occurrence is this occurrence. So this was 21, so now this becomes 21, this becomes 24, this is 21, and we have rotated this at this point. And now I'm gonna again keep a note on this, and now I have done a left rotation on this one. Now what I'm gonna do is I'm gonna go back in here and I'm gonna do the right rotation from the given node. So currently this is the node that I have pulled from the stack. When I passed in its left node for the left rotation. I passed in this node, and that's why I did the left rotation on this one. Now I'm going to stay here and I'm going to do a right rotation on this. So for the right rotation, what we do is we keep this as a temp key, and we store the key of this current node as a temporary key. This is the temp node, and whatever the occurrence it has. Now the current node's right is going to be the current node's left, that is this 24. That's going to be the right is going to point to its left, and the current key is going to be the left's key. So this is going to become 24, and this is because that's the 24 still points, its left still points to 24, and the left is going to be the right's left. So the right's left is 21. So that's what this is going to point to. This is going to point to 21, and the right's right is going to be, this is going to point to 21, the right's left. So the left is going to be the right's left, and the right's left is going to be the right. So the right's left is going to be the right's right, which was this. So this, it points to this, and the right's right is going to be the temp, which is this key, which is this node, sorry. So I move that here, and the right key is going to be 30. So instead of 24, we are going to put 30, and this thing remain as it is. So the 21 goes here, and the left still points to 20. Now we have to change the heights, because this here is not right. This is supposed to be 1. So what we do is we go here and we store the height of the current node's left. So this is the current node, and its left is 0. The height of that is 0. So we store that, and we say the current node's left height is going to be the temp height plus 1. The current node's left height is going to be the temp height plus 1, which is still 1, so this is perfect. And the current node's right height is going to be the stored height plus 1, that is temp height plus 1. So now this becomes 1, because the stored height was 0, so that plus 1 is 1, and the temp height, the current node height, is the stored height, that is 0 plus 2, that is 2. So this is perfect. So now as you can see, this is perfectly balanced. So now what we do is we go back and pull one more from the stack, and now we head at this node, and if you see that the difference between its children's height is -1, so this is perfectly balanced, it's within the range. So now we have a balanced tree, and the right and the left rotation is just based on how the heights are. So let's say if the left side was smaller than the right side by a factor of 2, or by a difference of 2, we would have taken this. So we would have first done the right rotation, and then we have done the left rotation. If the right's right height and the difference between the right height and the left height was mere 1, then we would have done only the left rotation and done the height balancing. The same thing goes for this. You have done the right rotation and done the height balancing. So this is how the insertion works. So this tree is perfectly balanced, considering that the height balance, the difference between each of the two nodes perfectly sits within the given three ranges, that is -1, 0, or 1. So basically the range of -1 to 1, both sides inclusive. So now let's see how you do a deletion in this case. So now I want to delete 30 from this node. So how do you do that? So what you do is, you first see if a given node is null. If from a given node, if the left side is null, that means there is nothing in the tree. So you just return null. There is nothing to delete. If the right side is null, then you return the left node, or you return the given node, because that's the only node and you set its left to null, and there is the tree is again empty. Else you set the current node, you take this as the root node, and then you go down to the tree that you want to delete. You also keep track of who its neighbor is or who its sibling is. So once we come down to here, this is the other node, this is the node that I want to delete, and this is the upper node. So it's the same idea here. As we go down, we keep on pushing things onto the stack, so that once we have to come back, we pop things from the stack and then we rebalance if it's necessary. So now we keep on rotating, we keep on executing the while loop. So it's the same code as in before, that once we delete something, so the deletion works in this way. We go here, what we do is, since this is the node we want to delete, we copy the data from this node onto this node. So now this becomes 24 and this becomes 0, and we also delete this node, so we no longer require those two nodes. And we pop up 1, we no longer require this node either. This is perfectly fine. So we pop up 1, we change the height of this. Well, the height of this is going to be 2 because we are just deleting this. We are just deleting things here. This still has a 2 in it, and this is perfectly balanced, because if you see the difference between the heights of these two, it's within the range. And the same idea goes here. We check the left's height with the current node's right height. If it's 1, then we go and do the right rotation, and then we carry out the height balancing, or we change the heights, or we do the left rotation with its left child and then the right rotation with the given node. If the difference between its left and right is -2, well, the above one was the difference was 2. In this case, if the difference is -2, then again I check which of the statements I want to execute. If it's again the right's height, and the difference between the right child's height is and that of the left child's height is 1, then I execute this. I do the left rotation on the given node, and then I balance the height. Else I do the right rotation on the given node's right child's height, on the given node's right child, and then I do the left rotation on the given node. So the right rotation on the right child and the left rotation on the current node, and then I do the rebalancing. Else I just increment the height wherever they are necessary, and I go to the next node. If the old height is the same as the new height of the given node is same as the old height, which I am actually storing here when I come out, or when I get the height, that means there is no more to rebalance. So I set the mark to finish 1, and I exit the while loop. So the while loop exits if there is nothing on the stack or everything's perfectly balanced, and then I return the object that I want to delete. Now, since the Radix sort has 2 trees as compared to the previous time when we used linked list and we only used 1 list, in this case I'm using 2 trees. So every time I take a tree, every time I'm trying to iterate through the numbers, what I'm doing is I'm taking from the first tree and I'm putting it onto the second tree. And so here initially for the first iteration I'm putting everything on the first tree, and on the second iteration I'm taking the things from the first tree and I'm putting it onto the second tree, and then at the end I'm just pointing the first tree to the second tree and setting the first tree back to null. So all the data there is gone. Since Java has its own garbage collection, there is no memory loss there. So in this case, what it does is it copies the left and the right of the second tree onto the first tree, so everything below that also gets copied over. Then I increment the number that I have covered, till how many units I have covered the number, and then I increment it until I exhaust the largest number that I have got in this, which is I have the max length of a number. For more detail, you can check the previous video. I have explained it more in detail there, how the Radix Sort works. This was just the implementation of the leaf of how the height balance tree works. So when I execute this is what it looks like. We have created 20 random numbers from -20 to 20. That's our range. And now the first iteration, I'm basically putting everything in bucket 0. So this has bucket 0 since the unit, it's going to look at the units only the units number. So this is -20. This has all the units places since the unit number is 1. It's all in here. This and so on and so forth. So this number is basically the minimum number that I have chosen as a placeholder for my root. So here the initial key is going to be a minimum number possible in the integer. So that's going to be a main number. So this is going to be overwritten if there is an insertion. Otherwise it's going to be replaced, or when there is a deletion, the minimum number is going to be placed back on to that thing, which is more like a placeholder. Here this is the second iteration. The buckets, again, the units number at the 10th number at this place is all 0. So this is all inserted in ascending order. The same thing for bucket 1, bucket 2, and so on and so forth. And this is the third iteration where the first bucket has all the data that you require. So this list is in the ascending order. As you can see, there is no 20 in this. So this list is in ascending order. All the other buckets are empty. As I stated again, as I also stated in the previous video, and here I'm saying again, we are doing 3 iterations because even though the size of the number is just 2 places, we are using the third place because of the negative numbers. If you ignore the negative numbers, you don't have to do the third iteration. You can just stop at the second iteration because the positive numbers in this case are already in ascending order. If you look at this 1, 5, and 9, and then you look at 11, these two 11s, 12, 13, 19, so on and so forth, they're already in ascending order. It's only for the negative numbers which are not in ascending order, I have to carry out one more iteration, and it gives me all the entire answer in the first bucket. Now the printing, what I'm doing with the printing is, so the print data. So I'm printing it in a recursive way. So I'm only printing the root 1. So everything on root 2 gets copied over to root 1 at the end of this, and then I try to do the insertion. In the original algorithm, I basically try to do the insertion from root 1 to root 2. So deletion in root 1 and then addition in root 2, or in second tree, deletion from first tree and addition to the second tree. So what I do in the print data is that I recursively iterate, and I go down until I know that I reach a leaf node, then only I print. So there is, if the occurrence is greater than 0, then I go in the for loop and do this, else I just print a key in this case. Well, in this case the occurrence is always 1 in the initially, so it's going to go in the for loop. And then I go to the left. I keep on going to the left because I want to go from the smallest to the largest. So I go on to the left. I print from left to right. You can also print from right to left. You just have to reverse the order in this. So if I basically reverse the order from here and I put it in here and then I print it, we are going to get this. We basically are going to have, well, there are 2 zeros in here, interesting. So we are going to have if you look at the final answer, we are going to have a descending range from the largest to the smallest. So it's just the printing matter, that how you want to print it. At this point we are just going to keep from the smallest to the largest. These are the numbers that we have created or generated randomly, and this is the final solution. So if you like this video, please comment, share and subscribe, and see you guys in the next video. Thank you.